we know if a molecule is polar or not? Well, polarity is the difference in electronegativity that leads to electrons being unequally shared between atoms. So in order for us to understand polarity, then we must understand electronegativity. Electronegativity is the tendency of an atom to attract electrons. Or you can think about it this way. Electronegativity is how well an atom can pull electrons closer to itself. So the more electronegative that an atom is, the more it's going to be pulling those electrons closer to itself. When looking at the periodic table, you can see that electronegativity increases from left to right and from bottom up, with the noble gases being the main exception. If you remember that fluorine is the most electronegative atom, then you can remember the pattern, which would be then increasing in electronegativity in this direction. I like to compare electronegativity to strength. The more electronegative that an atom is, or the stronger that an atom is, the stronger it's going to be pulling those electrons closer to itself, or the more electronegative that it is. If we have a difference in electronegativity within a molecule, meaning that those electrons are being unequally shared because one atom is more electronegative or stronger than the other, then we're going to have a polar molecule. Let's do a silly example. Let's assume that I have an identical twin, which I don't, unfortunately, but if I did, say that we go to the gyms on the same days, we eat the same meals, we do the same workouts, so we are exposed to the same environment and we have the same DNA. So hypothetically speaking, we will be equally strong. And say that we're holding hands and I pull as hard as I can in this direction and she's pulling as hard as she can in the opposite direction. I would ask you, in what direction would the net pull be? None, right? There would not be a net pull. You don't even have to take physics to understand that if we have the same force in opposite directions, there's not going to be a net movement. So with this example, we are equally strong, so we have the same electronegativity, and we are both pulling, but there's no net movement. Right? I'm not pulling the electrons closer to myself and she's not pulling the electrons closer to herself. The electrons will be shared equally among the two of us. And therefore, because the electrons are being shared equally, we would not be polar. But let's assume that I find somebody from kindergarten, and I like to assume that I'm stronger than a child from kindergarten, and say that we're holding hands and I pull this way and the child pulls in the opposite direction. Where are we going to be moving? In my direction, right? I'm going to be moving the child this way. So in this example, we would be polar because I'm more electronegative, I'm stronger, and I'm going to be pulling those electrons closer to myself. And for that reason, because we have unequally shared electrons, we will be a polar molecule. An American chemist called Linus Pauling assigned electronegativity values to elements. We can see those values reflected on this periodic table. If we're trying to find out if a bond is polar or not, we can look at the values of each atom and find the electronegativity difference. If the electronegativity difference is lower than 0.5, the bond is nonpolar. If the electronegativity difference is higher than 0.5, the bond is polar. Again, these numbers are used in the Pauling scale for electronegativity. There are other scales for electronegativity, so these numbers are not definitive. Let's try some examples. First, let's look at a bond between oxygen and hydrogen. This is a covalent bond in which an electron pair is being shared. Looking over here at the values, we can see that oxygen has an electronegativity value of 3.5 and hydrogen has an electronegativity value of 2.1. If we find the difference of electronegativity in between oxygen and hydrogen, we are going to get 1.4. When an atom is more electronegative, it pulls electrons towards itself. And we have to remember that electrons are negatively charged particles outside of the nucleus of an atom. Therefore, the atom with the more electronegativity is going to have a partial negative charge to represent a greater electron density, meaning that the electrons are going to be closer to the more electronegative atom, and that atom would be more electron rich. The lowercase Greek letter delta, followed by a negative sign, indicates that the end of a bond has a partial negative charge. And this right here then will indicate a partially positive sign. When we have two opposite charges separated by a distance, a dipole moment occurs. The dipole moment is represented by an arrow, and that arrow is pointing towards the more electronegative or electron-rich atom in the bond. You can see that the end of the arrow resembles a positive sign. And you can remember that the positive side of the arrow is going to be near the least electronegative atom. Again, looking at the difference in electronegativity being 1.4, because it is greater than 0.5, then this bond would be polar. Let's go ahead and do another example. Let's look at a bond between carbon and hydrogen. First of all, let's go ahead and locate them in the periodic table. Right here we have carbon, and on the left we have hydrogen. Because carbon is farther to the right, we can already tell that it's going to be more electronegative. But also, let's look at the values. The electronegativity value of carbon is 2.5, and the electronegativity value of hydrogen is 2.1. We know that carbon is more electronegative and therefore is going to be pulling those electrons closer to itself. And because of that, is going to have a partially negative sign. For that same reason, hydrogen is going to have a partially positive sign because it's least electronegative and it's more deficient in electrons. Then we can draw a dipole to represent that. And the dipole is going to be pointing towards a more electronegative atom. In this case, it's going to be carbon. If we take the difference between these two values, the answer is going to be 0.4. 0.4 is lower than 0.5, the value that I mentioned earlier about being polar. And because it's lower, this bond is going to be nonpolar. Now let's look at a bond between fluorine and fluorine. First, let's go ahead and look at that in the periodic table. Fluorine is right here. Okay. And the values provided for the electronegativity is 4. And you might remember from before that fluorine is the most electronegative atom. So I'm going to write those values. And you can see that the electronegativity is the same. Therefore, this fluorine is not going to be pulling any stronger those electrons that this other fluorine right here. It's almost like my example of the twins earlier on. We have the same atom pulling equally strong, right, with the same electronegativity, and therefore we're not going to have a net dipole. And if we look at the electronegativity difference, 4 minus 4 is going to equal to 0. So this is definitely going to be nonpolar. Let's analyze one more example. Let's look at a bond between sodium and chlorine. And for this example, I'm going to be drawing the valence electrons. Chlorine has 7, and sodium has 1. Now let's locate them in the periodic table. We have sodium over here on the left-hand side, and we have chlorine on the right-hand side. Because chlorine is farther to the right, we already know that it's going to be more electronegative, but let's also go ahead and look at the electronegativity values. So for chlorine, the electronegativity value is 3.0, and for sodium is 0.9. So let me go ahead and write that down. If I find the electronegativity difference between these two values, the electronegativity difference is 2.1. So what's actually going to happen is, because chlorine is so much more electronegative than sodium, it's not just going to be pulling the electron closer to itself, like in the previous examples. But what it's going to do is actually steal the electron. It's so much more electronegative, or if you want to think about my example about strength, it's so much more stronger, right? So much more electronegative that it's no longer just pulling it closer to itself. It stole it. Because why not? So I'm going to go ahead and redraw that so that you guys can see how it looks like now. So we have chlorine over here with the 7 valence electrons that it had initially, but it also has now the valence electron of sodium. Now, because chlorine has gained an electron, right? It gained that. And electrons are negative, and we have one more. We're going to have a negative 1 charge. For sodium, because electrons are negative and it just lost an electron, it's going to have a positive 1 charge. Because since electrons are negative and you have 1 less, that is symbolized with a positive sign. So this is what is happening right now. Since sodium lost an electron to chlorine, we had a transfer of electrons, and that caused an ionic bond. So what we actually have here is an ionic bond. Looking at the electronegativity values, if you have a value or an electronegativity difference of about 1.7 or greater, you're going to have an ionic bond, or it is generally accepted as an ionic bond. So again, a difference of 1.7 or greater would indicate an ionic bond. And ionic bonds occur between a metal and a non-metal atom. And we can see over here how sodium is a metal and chlorine is not. Let's go ahead and do more examples, but this time, instead of just looking at one bond between 2 atoms, let's go ahead and focus on an entire molecule. And when we're focusing on an entire molecule, don't pay too much attention to the electronegativity values on the Pauling scale. Instead of that, just look at the whole molecule and draw the dipoles, and then identify whether or not those dipoles are being added up. So let's go ahead and get started. I have methane over here, and I'm going to go ahead and draw it out. After you draw out the molecule, Go ahead and draw the dipoles. And if you remember, the dipoles are going to be pointing towards a more electronegative atom. So in this example, it's going to be carbon. Looking at these dipoles, you can tell that none of them are adding up. All of them are pointing in opposite directions. For example, one is going to the left, the other one is going to the right, one is going down, and the other one is going up. If they were going in the same direction, then they could add up. But because they're not going in the same direction, then they would cancel out. And every time that the dipoles cancel out, we're going to have a molecule that is nonpolar. Another way that you can think of this is the following. You can look at each bond independently and see if there is one bond that is more electronegative than the other. So for instance, you can look at this bond and you can compare it to this bond. And you can do the same thing here and the same thing there. But just looking at this, we can tell that we have the same bond, right? We have carbon and hydrogen, carbon and hydrogen, carbon and hydrogen, and carbon and hydrogen. So because we have the same bond happening, we know that they're not going to be more electronegative than the other. This carbon and hydrogen bond right here is not going to be any more electronegative than this carbon and hydrogen bond right here. So we know that the electrons are not going to be pulled any stronger by this hydrogen or this hydrogen. So this example right here is kind of like my example with the twin. With my twin, I have right here carbon that is being pulled away by the same atom. And we know that if it's being pulled away by the same atom, that atom is going to have the same electronegativity. And because they have the same electronegativity or the same strength, if you want to think about that example, none of them is going to be pulling those electrons stronger to itself than the other. And for this example, again, it's going to be nonpolar. Let's do another example. Here we have carbon tetrafluoride. Let's go ahead and draw that out. After you draw it out, you can go ahead and also draw the dipoles. So again, the dipole is going to be pointing towards the most electronegative atom, in which this example is going to be fluorine. We can see that these dipoles are all pointing in opposite directions, and therefore they're not going to be adding up. And because they're not adding up, this molecule is also going to be nonpolar. Now you could look at this and just know that it's going to be nonpolar without having to draw the dipoles, because you can see how we have carbon being pulled away by the same atom. Right, so we have the same bond here, the same bond here, the same bond here, the same bond here, and we know that if we're looking and comparing the same bond, they're going to have the same electronegativity and therefore no electronegativity difference. And if we don't have an electronegativity difference, then the molecule is not going to be polar. Let's go ahead and do another example. And I'm going to go ahead and draw this molecule out. After you draw the molecule out, you can go ahead and draw the dipoles. So again, the dipoles are going to be pointing towards the most electronegative atom in that bond. So we have a bond right here between hydrogen and carbon, and between these two atoms, carbon is going to be the most electronegative, and therefore our dipole is going to be pointing carbon. Again, same thing here. Same thing here. And carbon and fluorine, comparing these two, fluorine is the most electronegative atom, so we know that it's going to be pointing in that direction. However, you want to draw your dipole in a way that it represents that this bond right here is much more electronegative than this bond right here. So there we go. Now, looking at these dipoles right here, we can see how these ones that are going in opposite directions are going to cross out. But these ones, since they're going in the same direction, they would add up. And the net dipole is going to be going in that direction. If we have a net dipole, that means that we are going to have a polar molecule. Now, you could also apply what we talked about in the previous example, and you can look at this bond right here, and we know that this bond and this bond and this bond is the same. So let's compare then this bond to this bond right here. We know that this bond right here between fluorine and carbon is going to be more electronegative. So it's going to have the greater electronegativity difference than carbon and hydrogen. And because we have a great difference in electronegativity, we have, if you want to think again about the example of strength, we have one atom right here pulling those electrons much stronger than hydrogen right here. The molecule is going that way, right? Fluorine is so electronegative that it's pulling those electrons closer to itself in that direction. If that is the case, then you're going to have a polar molecule. And this will be more similar to that example that I had, me pulling the hand of a kindergarten child. I will be much more stronger, more electronegative, just like fluorine right here, and pulling the child, or in this example, fluorine is going to be pulling those electrons closer to itself than any of these other bonds or atoms within these bonds. Therefore, we're going to have a polar molecule. Now let's go ahead and look at carbon dioxide. I'm going to go ahead and draw it out. Now let's go ahead and draw the dipoles. And again, we know that the dipoles are going to be pointing towards the most electronegative atoms. So between carbon and oxygen, oxygen is going to be more electronegative, and therefore we're going to draw the dipole pointing in that direction. And same thing here, right? We have carbon and we have oxygen, so it's going to be pointing in this direction. Now looking at these dipoles, they're pointing in opposite directions, and therefore they do not add up, so they would cancel out. That would mean that this is a non-polar molecule. Now you could have go ahead and looked at this and compare these bonds right here to these other bonds, and you can tell that we have carbon and a double bond to oxygen, and same thing on this side, carbon and a double bond to oxygen. So you could have just looked at this and remember my twin example. We have the same electronegativity this way, the same electronegativity in the other way, and because they have the same electronegativity, not one of these oxygens is going to be pulling the electrons closer to itself stronger than the other oxygen. And therefore, this right here would be a non-polar molecule. These dipoles will cancel out and there will be no net dipole. Let's do one final example and let's look at water. Last but not least, water is a famous example because everyone likes to talk about water when discussing polarity. When you look at the molecule, you can see that the water molecule has a bent molecular geometry, and that is because these two lone electron pairs right here are going to be exerting some repulsion on the two bonding hydrogen atoms. Now that we know that, let's draw the dipoles. Again, we know that the dipoles are going to be pointing towards the most electronegative atom. In this bond, we have oxygen and hydrogen. Oxygen is more electronegative, and therefore the dipole will be pointing towards it. Looking at the other bond, we also have the same bond, so the dipole is going to be pointing towards oxygen. Because oxygen is more electronegative, we know that the electrons in this covalent bond are going to be attracted to it. Or you can think of it this way. Oxygen is more electronegative, so it's going to be pulling electrons closer to itself. Therefore, oxygen will have a partially negative sign because it has a greater electron density, or it's electron rich. And hydrogen will have a partially positive sign because it is electron deficient or electron poor. Because the water molecule has a bent molecular geometry, you can see when looking at the dipoles that they are at an angle. The dipole moment is a vector quantity, and what that means is that it can be broken down into vertical and horizontal components, the y and x components. So let me go ahead and draw these out. Here we have the vertical components, and here we have the horizontal components. Looking at the x, or the horizontal component, we can see that the dipoles are pointing in opposite directions. Hence, they will cancel each other out. But looking at the y, or vertical components, we can see that the dipoles are pointing in the same direction. So these two will add up. And therefore, we would have a net dipole moment in the upward y direction. You might ask, do I always have to draw the vertical and horizontal components of an angled dipole to figure out if there will be a net dipole moment? And the answer is not necessarily. You can look at it and recognize that due to the lone pairs in the central atom, the dipoles are at an angle, and therefore you will have a net dipole moment. In conclusion, having lone pairs in the central atom will cause the dipole moments to be at an angle, leading to a net dipole moment and the molecule being polar. I hope that you guys found that video helpful. If you have any questions, leave me some in the comment section. Other than that, thank you guys for watching, and I will see you in the next video.